Good afternoon, everyone. Firstly, I'd like to thank you all for being here today. Just to introduce myself, my name is Felicia Monti and I'm a doctorate student at the Sapienza University of Rome. Today, I show our work, which deals with the authentication of PRISMA images. PRISMA data became available since May 2020, and the studies conducted thus far focused on the possible hyperspectral application using data that has already been georeferenced. However, it's necessary to verify their geolocation accuracy. In fact, the Italian Space Agency currently declares 200-meter geolocation accuracy of the panchromatic and hyperspectral products, which it plans to improve to half pixel, so about 15 meters in the near future, by introducing a geometric treatment of the PRISMA products. Such poor accuracy can also create problems with the hyperspectral data application. For example, in the comparison between satellite data and field data. So during this talk, I'll describe our contribution on possible strategies for the geometric treatment of PRISMA panchromatic products. We have tested the following authentication methods. So the rigorous model and the rational polynomial function, both RPFs based on ground control points and RPFs calculated from the coefficient attached to the image. The geometric treatment was tested on 3 panchromatic images, level 2C PRISMA products, encompassing the area of Rome, Avezzano, and the island of Ischia. This choice was justified by their different topographical characteristics, given the importance of the arithmetic information in the authentication procedure. Therefore, both open source and commercial software were used. Several methods have been tested for exporting panchromatic data, including MATLAB or simply dragging and dropping QGIS and ENVI, while commercial software like ENVI and AutoEngine were used for the authentication. It's interesting to note that open source RTB library also allows for the geometric treatment of the panchromatic data. First, as is well known, the rigorous model is based on the collinearity equation, which relates the image space to the object space. This method requires knowledge of the parameters which describe the sensor and acquisition geometry of the satellite. But not all of this information are provided with the image. So, and currently, no software supports the rigorous model for PRISMA data. So we have tested the regeneric image file application in AutoEngine, which create orientation model reconstructed by providing some orbital parameters. And on the basis of the few PRISMA parameters available in literature, produce these unsatisfactory results. So we use the rational polynomial function with the coefficient attached in geocoding model section. To apply this coefficient to the image consistently, it's necessary to export the panchromatic data correctly. So in the raw matrix geometry, and verify that the raster is not geocoded. Therefore, we note that raw data are rotated 19 degrees with respect to the normal push-broom acquisition mode, and this is no trivial aspect which compromises our first test, in which we obtain grossly incorrect raw translation due to the incorrect export of data, panchromatic data in input. for the rational polynomial function with RPC application, we have collimated 20 points over each image and progressively set as ground control point to observe the trends of precision and accuracy. The results obtained on the island of Ischia were satisfactory. In fact, we can see a maximum accuracy of about 5 meters both in X and Y direction, calculated on the basis of the checkpoints. These trends of precision and accuracy are obtained using MV software, which applies to different transformations depending on the number of ground control points. With 1 or 2 ground control points, the rational coefficient are adjusted using an image space translation, while with 3 or more ground control points, the rational coefficient are adjusted using an affine transformation, so a rotation scaling and translation. Similar trends were also shown by the results of Rome and Avezzano, which, however, reach unsatisfactory results. In fact, we can see the accuracy values in both in X and Y direction. We have about 30 meters in the case of Rome in Y direction of accuracy, and about 20 meters in the case of Avezzano. The reason for these differences is the different treated areas. In fact, the island of Ischia covers only a part of the acquired image, a part of extension of 10 kilometers by 8 kilometers about. So, on the basis of these considerations and past experiences, we decided to concentrate our test on an area of similar extension on the image of Rome, and we obtained satisfactory results in the order of 1 to 2 pixels for the accuracy values. On the basis of past experiences, we also decided to treat the image for strips along the east-west directions and north-south direction. And we had sometimes observed that some images acquired with push broom acquisition mode produce better results when working on a few lines. So first, we expected that east-west direction works better. In contrast, we note that along north-south direction, working along north-south direction, we obtain better results. In fact, we can see an improvement in the accuracy in Y direction, which reach 5 meters of accuracy. Also, the rational polynomial function was tested despite its disadvantages. The determination of the rational coefficient was carried out with Ortho engine based on 60 points homogeneously distributed over the image and divided into 47 ground control points and 13 checkpoints. The results show that the calculation of 6 coefficient has reached maximum accuracy of less than 5 meters, and we can also see that the accuracy trends worsen as the number of coefficients to be estimated increases. This behavior shows that the first order function with 6 coefficient returns the best model of the PRISMA's images. In conclusion, to perform the geometric treatment of the PRISMA panchromatic image using the rational polynomial function approach, using also the RPC, so the coefficient attached to the image. It's necessary to ensure that the data are exported correctly, so in the raw matrix geometry. And as we can see from the trends of precision and accuracy, a minimum of 6 to 7 ground control points provide statistically significant values of precision and accuracy. A valid alternative is the rational polynomial function, which requires more ground control points, but given the medium resolution, so the spatial resolution of the panchromatic image, the ground control point can be acquired directly from vectorial cartography in height or medium scale, which is now available over the entire European territory. Finally, we think also that with more rigorous information on orbital and orientation parameters of the PRISMA image, even better results could be obtained with the rigorous model. So I have concluded. Thank you all once again for your attention.